Hello everyone and welcome back to my YouTube channel. This is the fifth lecture on the series of matrices, and this lecture is a continuation of part 1 of types of matrices, which is already uploaded in the matrices playlist. This is where you are going to find this lecture part 1, and in this part 1 we have discussed the basic types of matrices, such as what is row matrix, what is column matrix, what is diagonal, what is square matrix, what is identity matrix, symmetric matrix, skew symmetric matrix, etc. So basically these are the concepts which are the foundation for today's lecture. So if you have not watched this part 1, I highly recommend you to go through it first. I'll attach its link in the description box as well as in the I tab so that you can directly access it from there. Now in today's lecture, we are going to discuss the remaining special types of matrices, that is upper triangular, lower triangular, Hermitian, Skew-Hermitian, orthogonal, unitary matrix, normal matrix, idempotent, involutory and nilpotent matrix. And all these matrices are very important for the exams, whether it is your university exam or the competitive examination point. So without wasting any more time, let us begin today's lecture. So first type is upper triangular matrix. First of all, it is a square matrix, and in this matrix we have the condition that elements below the main diagonal will be 0. That is, if you have a matrix defined like this, then Aij will be 0 if your index I is greater than j. Means what? Suppose we have this as the generalized matrix with in general elements defined in it. Now if you observe, we are writing the indexes Aij. Now I am saying that Aij will be 0 if I is greater than j. Now if you observe, all the elements mentioned in this triangle, the lower triangle, have the ith index greater than j. That means 2 is greater than 1, 3 is greater than 2, 4 is greater than 3, 3 is greater than 1. So all the elements mentioned in this lower triangle are the elements satisfying the condition that I is greater than j, and all these elements in upper triangular matrix will be definitely 0. Aij will be 0 for all these elements since they are satisfying this condition, right? So what is upper triangular matrix? It is basically that square matrix in which all the elements below the main diagonal are definitely 0. What is your main diagonal? This is your main diagonal, and all the elements lying below this line will be definitely 0. We are not saying anything about the upper side elements. We are simply saying that all elements below the main diagonal are 0. Many students get confused and say that upper triangular matrix is that matrix in which all the elements in the upper triangular are non-zero, but this is not the condition. Upper triangular matrix emphasizes the condition for 0 elements. Which elements are 0? The elements below the main diagonal are 0. This is the condition. I hope you will not make mistake in this definition. In a similar way, we have the definition of lower triangular matrix. Again, it is a square matrix in which all the elements above the main diagonal are 0. What is your main diagonal? This is your main diagonal, right? So all the elements above this line will be definitely 0. And what is the condition for these elements? It is the condition that I will be less than j. If you realize, in this generalized matrix, the index I is definitely less than j. 1 is less than 2, 1 is less than 3, 1 is less than 4. Likewise, every element mentioned in the upper triangular side satisfies the condition that I is less than j. So for lower triangular matrix, what is the condition? These all elements will be 0. That means all the elements in the upper triangular side are 0 elements, and there is no restriction on the lower triangular elements. So if I ask whether a null matrix, if I define a null matrix like this, 0 0 0 0 0 0, every entry is 0, can we say that this is a upper triangular matrix? Many students will say that this is not upper triangular matrix, but let me tell you, this is upper triangular matrix also, and this is lower triangular matrix also. Why? Because for upper triangular, the elements below the main diagonal must be 0. Are they 0? Yes, they are 0. So this is definitely one upper triangular matrix. And for lower triangular, if I ask, are the elements above the main diagonal 0? Yes, they are 0. So this also satisfies the condition for lower triangular. So one null matrix is upper triangular also and lower triangular matrix also. In fact, every diagonal matrix is upper triangular matrix also and lower triangular matrix also. I am telling you about this scenario. If you have a condition like this, this is your upper and lower triangular both, right? So I hope the basic definition of upper and lower triangular is clear to you. Now let us move to the third type, that is Hermitian matrix. Okay, for Hermitian matrix, you must know what is conjugate transpose. So, a square matrix is called Hermitian matrix if it is equal to its conjugate transpose. मतलब अगर आपके पास कोई भी एक मैट्रिक्स A दिया है और अगर आप उसका conjugate transpose निकालते हैं, अगर वो दोनों सेम आए, मतलब A conjugate transpose अपने सेम मैट्रिक्स के बराबर आ जाता है, तो हम ऐसे मैट्रिक्स को हर्मीशियन मैट्रिक्स बोलते हैं. एंड हाउ डू यू डिनोट द conjugate transpose for any matrix? So if this is your defined matrix A, then A conjugate transpose, how do you denote the transpose? You define the transpose by AJI, and conjugate is defined by bar. So conjugate transpose A is defined like this, AJI with bar. So a square matrix is said to be Hermitian matrix if it satisfies this condition, right? For every I and j, means it should satisfy this condition for the diagonal elements also, right? We have one note written here that diagonal entries of a Hermitian matrix are always real. Why you are having this condition that diagonal entries are always real in Hermitian matrix? See, this condition must be satisfied by every element, so it should be satisfied by diagonal entries also. So how do you denote the diagonal entries? You define by AII, where your index I and j is same along the diagonal line. So AII should be equal to AII conjugate, right? Let us say that we are having the complex entry along the diagonal line. So I am saying that this is one of my diagonal elements. So if AII is x plus iota y, then what will be x plus iota y conjugate? It should be this. And what will be the conjugate? It will be x minus iota y. Means what? X plus iota y should be same as x minus iota y. This x will get cancelled. So we have 2 iota y equal to 0. But 2 iota is a non-zero number. So definitely my y has to be 0. So in a complex number, if your imaginary part is 0, that means what? X plus iota 0. And that is x, means this is only a real part. What it means? It means that all the diagonal entries in the Hermitian matrix will be definitely 0. So if you are taking a complex number here, it is never going to be one Hermitian matrix. Fine. So suppose this is your given example, and if we have to prove whether this is a Hermitian matrix or not, let us find the conjugate transpose of this matrix. So what I will do, I will apply conjugate and transpose at the same time. So what is the conjugate of 2? It is 2 only. And what is the conjugate of 3 plus iota? It is 3 minus iota, and I have to apply transpose also. So this 3 minus iota will be considered at this place, and this will be 3 plus iota and 5, and we can clearly see that this is the same matrix A. So this is one of the examples of a Hermitian matrix. I hope this is clear. Fine. Now moving to the next type, that is Skew-Hermitian matrix. So a square matrix is called a skew-Hermitian matrix if it is equal to negative of its conjugate transpose. Means if we take the conjugate transpose of any matrix, then it will be negative of the matrix itself. That means Aj conjugate will be equal to negative of Aij. And what will be the note here? Diagonal elements in skew-Hermitian matrix are purely imaginary or zero. Why? Suppose this is the condition satisfied for every I and j, means it will be satisfied for the diagonal elements also. Let us apply on the diagonal elements. So it will be Aii conjugate minus Aii. Let us say that our complex element is x plus iota y. Conjugate, this will be negative of x plus iota y, and apply the conjugate here. It will be x minus iota y equal to minus x minus iota y. Now if you realize minus iota y is getting cancelled, so we have 2x is equal to 0, implies x is equal to 0. Means in the diagonal elements your real part is going to be 0. That means 0 plus iota y. That means what? We are only having elements of the form iota y only. So this can be either purely imaginary or it can be a zero complex number, right? So keep this in mind. In skew-Hermitian matrix, diagonal elements are either purely imaginary or they are zero. So let us quickly verify whether the given example is skew-Hermitian matrix or not. So quickly find out what is the conjugate transpose of this matrix. So what will be the conjugate transpose? It will be 0, 1 minus iota, 2 plus iota, minus 1 minus iota, 0, 3 minus 2 iota, minus 2 plus iota, minus 3 minus 2 iota, and 0. Now just take minus common from here. What do we get? 0, 1 plus iota, it will be 2 minus iota, minus 1 plus iota, 0, 3 plus 2 iota, minus 2 minus iota, and this is minus 3 plus 2 iota and 0. And this is nothing but the same matrix A. So we can see that conjugate transpose is actually negative of A. Hence it is a skew-Hermitian matrix, right? Now moving to the next type, that is orthogonal matrix. What is orthogonal matrix? A square matrix is said to be orthogonal if P into P transpose or P transpose into P gives me the identity matrix. Any matrix satisfying this condition is always known as orthogonal matrix. So given this matrix P, let us verify whether this is a orthogonal matrix or not. So first of all, we are going to find P transpose. What will be P transpose in this case? It will be cos theta minus sin theta, and cos theta. Now you just quickly multiply P and P transpose. What will be P and P transpose? Cos theta into cos theta will be cos square theta, minus sin theta into minus sin theta becomes plus sin square theta, cos theta sin theta into sin theta minus sin theta into cos theta. And same way we have sin theta cos theta minus sine theta cos theta, and this will be sine square theta plus cos square theta. And on simplifying we know that cos square theta plus sine square theta is 1, and this is cancelled. This is also cancelled. So we have 0, 0, 1. So this is nothing but your identity matrix of order 2. In the same way, when you will find P transpose into P, you will realize that this is also one identity matrix. So what we can say, the given matrix is one orthogonal matrix, right? Now what is the next type? This is one unitary matrix. What is a unitary matrix? A square matrix is called unitary matrix if conjugate transpose of u into u or u into conjugate transpose of u is always the identity matrix. Let us quickly verify this result. So this is the given matrix. If I find conjugate transpose of this matrix, what I have, it will be 1 by root 2 minus iota by root 2 minus iota by root 2 and 1 by root 2. So u into u transpose conjugate will be what? 1 by root 2 into 1 by root 2 is 1 by 2. This will be minus iota square by 2, and then we have minus iota by 2 plus iota by 2. This will be iota by 2 minus iota by 2. This will be minus iota square by 2 plus 1 by 2. And on simplification we get 1 by 2 iota square is minus 1. So this will be half plus half 1. This is cancelled, 0, 0, and this is also 1. So this is your identity matrix. And when you calculate u transpose conjugate into u, you will see that that is also one identity matrix. So from this result, since we are getting one identity matrix, we can say that the given matrix is one unitary matrix. Next type is normal matrix, right? So a square matrix is called normal matrix if it commutes with its conjugate transpose, that is B conjugate transpose B into conjugate transpose B is same. I am not saying that it is going to be equal to identity matrix. If this scenario happens, it will be known as the unitary matrix. In normal matrix, what we are saying that it simply commutes with its conjugate transpose, right? So let us verify whether the given matrix is a normal matrix or not. So we are going to find what? We are going to find conjugate transpose of B. That will be what? 1 minus iota and 1. Now quickly finding B into B conjugate transpose, that will be what? It will be 1 plus 1. This will be minus iota plus iota, iota minus iota. This will be minus iota square plus 1. And this is equal to 2, 0, 0 and 2. Next, in the same way, if we find B conjugate transpose into B, that will be what? It will be 1 minus iota square and then iota minus iota, then minus iota plus iota, and this will be minus iota square plus 1. And if you simplify this will be 2, 0, 0 and 2. And since we can see that this result and this result is same, so we can say that conjugate transpose is commuting with the same matrix B. So we can say that B is one normal matrix, right? Next important special type is idempotent matrix. This is very important matrix and this is frequently asked in the competitive exams. It has numerous properties. So this is one of the important special types which we are going to study in today's lecture. So what is the definition? A square matrix B is called idempotent matrix if its square is equal to the same matrix itself. right? So means if you perform the square of any matrix and it comes out to be the same matrix, then it is known as idempotent matrix. Fine. So if this is the given matrix, quickly find its B square. B square means what? You are multiplying the same matrix with itself. So that will be what? 1 0 0 0 into 1 0 0 0. Now perform the matrix multiplication. What do we get? This will be 1 and this is 0. This is again 0 0, and we can see that this is the same matrix B. So we can say that B is one of the idempotent matrices. In a similar way, we have the next important special type of matrix, that is involutory matrix. And involutory matrix says what? If your square of the matrix comes out to be the identity matrix. In idempotent, you were getting the square equal to the matrix itself. In involutory matrix, you get the square equal to the identity matrix. Then only you call that matrix as involutory matrix. So if this is the given matrix, we are going to verify whether this given matrix is involutory or not. So multiply this matrix with itself. What you are going to get? It will be 0 1 1 0 into 0 1 1 0. So what do we get? We have 1 0 into 0 plus 1 into 1 1. This will be 0 and this is again 0 and this is 1. So this is nothing but our identity matrix of order 2 cross 2. So we can say that since square of the matrix is coming out to be the identity matrix, this is my involutory matrix. Now the last special type for this lecture is nilpotent matrix. This is also frequently asked in the competitive exams of mathematics. So nilpotent matrix says what? A square matrix B is called nilpotent matrix if for some positive integer k b power k comes out to be 0. मतलब आपको कोई एक पॉजिटिव इंटीजर k ऐसा मिल रहा है जो b की पावर k करने पे 0 बन जाए, 0 मैट्रिक्स बन जाए. 0 इज नॉट द 0 नंबर, इट इज द 0 मैट्रिक्स, राइट? मतलब आपको कोई एक ऐसा पॉजिटिव नंबर मिल रहा है जो b को उतनी बार मल्टीप्लाई करने पे आपका आंसर एक 0 मैट्रिक्स आएगा. सपोज दिस इज द गिवन मैट्रिक्स. इफ आई ट्राई टू फाइंड b square, so let us find b square first of all. So that is what? 0 1 2 0 0 3 0 0 0 multiplied with the same matrix 0 1 2 0 0 3 0 0 0. And what is this answer? It will be 0. This is again 0 and this is multiplied, so it will be 3. This is again 0 0. This is again 0 0 0 0. This is basically your b square. And if you find b cube, that means b square into b. What do we have? 0 0 3 0 0 0 0 0 0 multiplied with the matrix b 0 1 2 0 0 3 0 0 0, and this is equal to, what do we have? This is 0, this is again 0, this is again 0 0 0 0. Basically this is one null matrix. Means what we have got, if we are taking third power of b, we are getting a 0 matrix, right? So that means there exists one positive integer k such that b power k is 0. Means this matrix is satisfying this condition, hence we will call it as nilpotent matrix, right? So this is all about today's lecture. I hope you have understood all the special types discussed in this lecture. All the types are very important. So please go through this video once again. If you have any query, or you can just comment your queries in the comment section. I'll just go through your queries and answer to it. Please like and share this video if you have understood this video. I am going to post the upcoming topics of the matrix series in the next few weeks, and do share and subscribe so that I can help you in understanding the concepts of mathematics very easily. Thank you so much.